Stereo Police, happy Sunday, at least it is for me. And back with, this is going to be a three-part series. This is part two on myths regarding speaker cables. And I covered at least a couple of myths last time. And today we're going to talk about oxygen-free copper. And quite frankly, there's no such thing in reality. So when you see oxygen-free, there should always be a percentage next to it or near to it, because during the mining process and during the manufacturing process, there are many impurities introduced in the copper. Oxygen is only one of them. Other elements are in there, and then there are certain levels of impurities that are acceptable based on ASTM standards, and there are some European standards, and we'll talk about a couple of those in a minute. And there are different requirements depending on what one is doing with the copper. For example, in the field of semiconductor manufacturing, when you're actually using copper for, at the micron level, it needs to be pretty pure. When you're working in clean rooms and that sort of thing. But for standard lamp cord, that you buy at Home Depot or Lowe's, there's not such a requirement. And then there's everything in between. So I just pulled this randomly. There's no particular reason I pulled this other than it's inexpensive speaker wire. It's probably a good product. I have nothing bad to say about this. That's not why I pulled it. I just want to demonstrate a reasonably priced product that alleges to be oxygen free. And they say that it's greater than 99.95% pure. Now, a lot of people get caught up in these numbers and what's that really mean and what effect does that have, in a speaker cable on sound. I'll get to that in a minute, but what does this really mean? And what ultimate effect does this have on, well, what do we really care about in speaker cables? Well, for me, the main thing, besides, and I'm going to get into this, I want to say some positive things we actually want to look for in speaker cables, and I'll get into that in part 3. But the main thing we want is a low resistance cable. And of course, the positive things I'm going to say are about durability and quality and quality of construction and good connectors, and that sort of thing. But, we want a low resistance cable. Now, and that's where a lot of manufacturers tout this business of being oxygen free. So let me go to another cable, and this manufacturer touts 99.99998% using this standard right here, UPOCC. This is a Japanese company that has their own special manufacturing process. So one might look at this and go, whoa, it's got to be great. And this particular cable is, in the range of $500 to $700 for couple of meters. And then there was another company, and I'm not going to name names. I don't want to disparage companies. I'm sure they're high quality products, and if someone can afford them, that's wonderful. Go buy them. All I'm trying to do is educate consumers, my subscribers, uh, just know what you're getting and know what is, know what's of value and know what makes a meaningful difference. There was another company I found that had, standard couple of, 3 meter, 6 meter speaker cables for $6,300, roughly. And once again, they had this 99.99999% number in there. And they also gave a velocity of propagation of 96%. And I think a lot of people look at, and there were some other specifications they gave, and people browse websites and look at things quickly and are often wowed by these things. But do you ever really stop to wonder what these things are, what they mean? Well, I'm going to talk about this right here in part 3, but this is just the velocity of propagation of charge, not the speed of the electrons. Okay, it's not like the electrons are moving down the wire that fast. This is the velocity of propagation of the waves of the charge in the wire, not the electrons. You'll know that from Audiophile University Part 1. As the charge moves down the wire, not the electrons. Remember, electrons zigzag and even go backwards sometimes. But ultimately, the charge will propagate down the wire at 96% of the speed of light. Light in a vacuum travels at the speed of light. But anytime charge, for example, propagates through a medium of some kind, other than a vacuum, it slows down. Because it hits things. Okay. And velocity of propagation is meaningful for electrical engineers, especially at radio frequencies and in communications. Because, when you send a signal down a very long wire, it's not going to arrive at the end of that wire instantaneously. There's going to be a delay because of this velocity of propagation. And, this is meaningful when you have, wires that span miles and miles and miles, hundreds of miles. Now, is this really meaningful for a 3 meter a 3 meter piece of wire? Where's Stewie? I need Stewie to laugh. If you want to do something just for fun, go look at the speed of light. I might do that right now. I might do that. You know what? I might do it at the very end and not even bother with dealing with that in part 3. I think part 3, I want to make a positive video about speaker wires. I might do that at the end. This is going to be fun. Let's find out how long. But anyway, so velocity. I'm on a tangent, but this is useful. Velocity of propagation. 96% is fairly typical for a lot of wires, especially coax cable. And then some wires will be in the 60% range, and some wires are 96 is pretty high. That's pretty high for a wire. Some, like I say, some will be in the 60%, on up to that 96% number, and there are many factors involved, like the dielectric material used, and many other factors. it doesn't affect the signal itself other than the speed that or the time it takes for the charge to arrive at the end of a very, very, very long wire. So 3 meters, 6 meters, does this make a difference? I don't think so. The speed of light is very, very, very fast. And even if I had a wire that was, let's say I had a really awful wire that had a velocity of propagation of 80%, and I compared that to 90%, which I might do, what would be the difference in time it would take when that signal left the back of the amp and reached my speaker? And does a delta T or a delta time have any effect on the sound? It's just a time difference. Okay, back to oxygen free. All right. So there are standards, ASTM standards. There are European standards, and there's that Japanese company that has their own thing going on. So let's talk about a couple of standards here. I have sources for everything. There are different grades of copper, and this is a C10200 grade. This is a fairly low grade. This would be sort of, well, this is not the lowest grade, but 99.95% pure. Right here. That's probably what they're using. That's why how they came out with that number. See? Well, no copper is ever 100% pure. And here's another grade, C10100, that's 99.99% pure. And it has a slightly higher percentage of electrical conductivity. We're going to talk about that in a minute. Pure copper, this is according to this website. I'm not in the copper business. Has a minimum copper content of 99.3, and it's known as commercially pure copper. Then we get into oxygen-free copper. It's a refinement process, and according to this website, the purest commercial copper grade is 99.99. You know, superconductivity, X-ray tubes, printed circuit boards, etc. need a purer grade copper. Great. So we have these standards here. We have the high standard of 99.99, and I've got this lower standard here, C1100. It's the lowest one I could find, 99.9. We're going to bounce these two off of each other in just a minute. And that Japanese standard I was showing you earlier, the 99.999999999%, the UPOCC wire. Here's, if you want to read this, you can. I found this on this website. I couldn't find much else about it, but it was patented by some professor, and it achieves this incredible standard. And I guess some companies use this, but does it really make a difference? It's probably expensive. Okay, and here's another thing you can read. You can pause and read this yourself. It's from another wire manufacturer that discusses impurities in copper, and it talks about the different standards. And it's interesting. So let me before I get into running some measurements and showing you something interesting about how these we're going to take the lowest grade and compare it to the highest grade here. And we're even going to compare it to that Japanese standard and see what effect that has on the resistance of a 3-meter length wire. But I'm going to give you an analogy. Sort of. I'm really bad at analogies. Everyone says my analogies suck, but anyway. I'm going to take this water purification system I have. One, everyone can kind of relate to this. Everyone wants clean water. It's $174. Eliminates up to 99% of solids and all this other stuff here. Some heavy metals. And we kind of want that, and I agree with it. And I want decent speaker cables too. What if some guy comes in and says, hey, I got a better system? It's going to be $300 and it's going to eliminate 99.01% of all that stuff instead of 99%. Well, if you're willing to pay double the amount of money for a 0.01% gain, if you think that's going to affect the taste of your drinking water and make a better odor or color or whatever, if that's what you think, that's fine. But then there's some other dude that comes in and says, hey man, I got this system for $6,666. It's going to bring it up to 99.1% filtration. You know, I don't know. And then, you know, I give you 2 glasses of water, one from this system, $179, and one from this system, and you're going to look at the color and smell the odor and taste the water, and, you know, we'll do a double blind test, and are you going to be able to tell the difference? Is one water going to produce better imaging and soundstage? I'll leave that for you to answer. Okay. So let's compare these things. So what we're going to do is my source. I have found the electrical resistivity. If you've attended Audiophile University, you'll know what that means. Of C101 and C111, C1100, 11000, and C10100. And I've got the resistivities here. I've taken the worst case scenario down here for the 11000, because there's another one here that's even better, but taking the worst case scenario right here, the one with the highest resistivity. And what I'm going to do, and by the way, this is the resistivity of pure copper, even though it doesn't exist. And I'll tell you what I'm going to do with that in a minute. So the resistivity of our lowest grade at 99.9% is 1.78. The resistivity of our better grade at 99.99% is 1.72. It goes down because it's it's a lower resistance per unit meter. And let's take 100% pure copper. So let's like that Japanese standard that achieves 99.9999. I'm not even sure I believe that, but I don't know what's going on there. I haven't researched it. But let's just pretend that Japanese standard achieves 100% pure copper. Let's give them the benefit of the doubt. So let's take it on down to pure copper. And let's assume, and you'll remember this from my previous video, let's assume we have a 3-meter length of speaker wire at 14 gauge. And 14 gauge wire has an area of this many meters squared. So we have the area, we have the length, and we have the resistivities. And that's the Greek letter rho. We have the resistivities of all three. We have them right here. So now we can measure the resistances of all three of these wires. And I got it. I already did it. So in our worst case scenario, we have 0.0256 ohms. And in our best case scenario, our pure copper, we have 0.024 ohms. And in our mid case scenario, 0.0248 ohms. These things are incredibly, I mean, if you're into electronics, these are such small differences. They're minuscule. I cannot for the life of me see how this makes any difference whatsoever. In any sense. I don't know how substituting this 3-meter wire for that one would have any effect on the sound, the ultimate sound of when you're listening to music at a reasonable level, or any level. I don't get it. And now, if on a positive note, if you want to be positive about it, you could do a percentage difference between the worst and the best case scenario. I have a percentage difference calculator here, so you don't have to believe me. You could say, well, look, there's a 5% difference, but 5.6% difference between the two. But it doesn't really matter, because we're talking about such minuscule values. Such tiny values. Does a 5% difference make a difference? And I'll wrap this up with one example. And this was like an afterthought, so I just scribbled it out. Let's say we have a 1 volt RMS signal, AC, going to, this is your speaker right here, going to your 8 ohm speaker. And we're going to consider it a resistive load for the sake of argument here. And then here's your 0.0256, your worst case scenario, speaker wire, 3-meter speaker wire, worst case scenario. And if you remember my previous videos about resistance in Audiophile University, we talked about the voltage divider rule. I'm not going to get into that, but we're going to find out how much voltage will be right here across your speaker. In other words, how much voltage is dropped by this resistance? How much power is lost due to heat, energy dissipation, in your speaker wire? And so, in other words, how much voltage will arrive at your speaker? We have 1 volt here. So running the voltage divider, we're going to have 0.9968 volts right here. Running the voltage divider. All right. Let's go to our best case scenario, 0.242. It's a lower resistance. This is our pure copper, which doesn't exist. Running the voltage divider, we're going to have 0.9969 volts right there. Now, 0.9969 versus 0.9968. Come on, guys. Come on. Really. Let's talk real world here. And the other thing is, and I won't prolong this point, but if someone makes an argument that, well, it's not really about resistance, we got our copper atoms, but it's these impurities in here, and these impurities are causing, the electrons to bump into them, and that's causing smearing or phase distortion or something like that. No, because you got to remember, and that's why the very first Audiophile University, I began with the fact that current is not the flow of electrons, it's the flow of charge. And the impurities, even in our crappy wire, this is lamp cord right here. It's 99.9% pure. it's like our original $179 reverse osmosis filter for, it gets 99% of everything out of it. I'm not sure what gains we're going to get. And given that it's charge that's flowing, and these electrons, even in an absolutely pure copper wire with no impurities, the electrons are still going to do this. And there's still going to be a drift velocity. And ultimately, it's the charge that's flowing in waves. That's the signal. So adding one part per whatever of impurities. I can't calculate the parts per million given 99.9%. I'm sorry, but adding a little impurity. How would I do that? If 99.9% pure, that'd be one impurity. Gosh, I couldn't even draw it. I mean, if we have a gazillion copper atoms here and there's one impurity, I mean, there's hardly any impurity. So how's this one little guy going to stop anything from happening? Again, the electrons are already doing this. I mean, it's so ridiculous. I struggle for words. And I'm just baffled by how anyone could think that this could affect phase and smearing or anything. It's charge, not electrons. And in terms of velocity of propagation, hold on a second. You know what? I will cover that in part 3. Hold on a second. Okay. What I've done here is I talked earlier about velocity factor, and I showed you a $6,000 cable company touting a velocity factor of 90%, meaning that whatever cable they're using facilitates charge flowing down that cable at 90% of the speed of light, which is typical of. It's not unusual. There's nothing special about that in the electronics industry. That's you can go buy coax cable from Home Depot and it'll achieve the same thing. But let's just say I have some really awful wire that I'm using for my speaker wires, and it has a velocity factor of 80%. I could have chosen 50 and or something like that, but I'm going to just choose 80 to be reasonable. And let's look at the difference. Now, velocity factor is just how fast inputting a signal at one end of the wire and how fast it'll travel down the wire. There's going to be a time delay before it reaches the end of the wire. Time, just simple time. Look at your watch, except these are very, very small numbers. So let's take the 90% example. And so velocity is measured, for example, in meters per second. So units of distance divided by time. So we have a 3-meter wire, and we know that, and what I've done is I've calculated, this is the speed of light up here in meters per second. So I've already calculated what 80% of the speed of light is right here, and I've calculated what 90% of the speed of light is. So I've already done that. So we have our 3-meter wire, and we have our 90% of the speed of light. So we want to know how much time it takes to travel down that. Well, we just rearrange this equation right here to time equals to length divided by velocity. All right. So basically, we take 3 meters and we divide it by our velocity of 90% of the speed of light, and we get it's an exponential of -8, but 0.0000001.1 seconds. Can you conceive of that number? So that's how long it'll take for your audio signal, with the time it exits, your binding post, by the time it arrives at your speaker binding posts, given this 90% velocity factor number. Let's do the same thing with our really crappy 80% velocity factor cable, whatever it is. And we get also an exponential of 10 to the negative 8. So there's the same number of zeros here, except we get 1.3 seconds. So 0, 0, 0, 0, 0, 0, 0, 0, 1.3 seconds. I'll leave it there. Is this a specification that makes a difference to you? Are you in a rush? If you're in a rush, maybe you want to spend the extra $5,800 on the cables, and then you'll receive your your signal there just this much faster. If you can perceive that increment in time. Now, does this have an effect on sound? You tell me how it does. Someone tell me how this has an effect on sound. There are other components in your system. Transistors, active components, have a delay as well. Your digital signal processing in your DAC has a much, the processing going on there they have time delays as well. This is nothing compared to that stuff. If anyone is concerned about this, I would say probably seek some talk therapy. That'll help. Stereo Police. Hope you enjoyed it. And let me just sum it up with a sort of a caveat here. I think speaker cables, it's nice to have good quality components with good banana terminators or spades or whatever, and things are going to last. I like gold plated. I want good quality components. I'm constantly using my cables, taking them out, putting them in. You want things that aren't going to break, and I like to have a good braiding on the outside. I like the looks of them too. It's part of its eye candy and all that. And I like reputable companies. I'll show you what my cables are later that I use. And that's all wonderful. And I encourage you to buy good quality cables, although if you want to use a standard monster cable, if you want to use a lamp cord of a high enough gauge, that's fine. I've done that too. I don't know that it makes a difference in terms of sound quality. So just be wary of a lot of these outrageous claims, about the snaps are snappier and the imaging and the phase distortion and all this stuff. I'm just trying to say I'm looking at the practicalities of this stuff, and I just can't see where any of this could have an effect on sound that could be actually perceived by the ear-brain combination. Psychologically, if you want to believe it, there are things that are psychosomatic medically, and there's something equivalent here in audio. But if you really want to believe it, and it makes you feel better, then I don't want to discourage you. But if you're really into reality, weird stuff like reality, and you want to know what's really going on, and you're like me, you question things, you don't just accept what someone tells you, and you want to get to the root of things, well, I'm trying to give it to you, and you make your own mind up. I'm not going to tell you what conclusions to reach. I'm just trying to lay it out, and if anyone has an opinion that differs, or if there's some facts or studies that I'm not aware of, I'd love to read them. Stereo Police. Ciao.